absorption refrigeration systems, and I mentioned that the two most commonly used refrigerant absorbent pairs are those based on water lithium bromide and ammonia water systems. In the present lecture, I shall discuss the absorption systems based on water and lithium bromide, and the specific objectives of this particular lesson are: introduce water lithium bromide systems, discuss property evaluation with the help of property charts, present steady flow analysis of the system, discuss typical problems associated with this system, and finally describe commercial systems. And at the end of this lesson, you should be able to explain basic principles of water lithium bromide systems, obtain relevant solution properties using property charts, evaluate steady state performance of the system, describe practical problems, and discuss commercial system practices. Let me give a brief introduction. Absorption refrigerant systems using water lithium bromide are extensively used in large capacity air conditioning applications. In these systems, water is used as refrigerant and a solution of lithium bromide in water is used as absorbent. Since water is the refrigerant, it is not possible to provide refrigeration at sub-zero temperatures. As a result, these systems are used in applications where the refrigeration temperature is above 0 degrees centigrade. And the analysis of this particular system is relatively simpler compared to the ammonia water systems, because the vapor generated in the generator is almost pure refrigerant, unlike ammonia water systems where both ammonia and water vapor are generated in the generator. In fact, I mentioned in the last class that if the boiling point temperature difference between the refrigerant and absorbent is very high, then only pure refrigerant is generated in the generator. This is the case with water lithium bromide systems, whereas in ammonia water system the boiling point temperature difference is not very high. As a result, in the generator you find that the vapor consists of a mixture of both refrigerant ammonia and also the absorbent water, whereas in lithium bromide systems only pure water is generated. As a result, you will find that the analysis becomes much simpler. That is the reason why we begin this discussion with water lithium bromide systems. First, let us look at properties of water lithium bromide solutions. The first important property is composition. Composition of water lithium bromide solutions, as I mentioned in the last class, can be expressed either in mass fraction zeta or mole fraction x. And the mass fraction zeta is defined here as the ratio of mass of anhydrous lithium bromide to the total mass of the solution. Here ml is the mass of anhydrous lithium bromide, that means pure lithium bromide, and mw is the mass of the water in the solution. You can also express composition in terms of mole fraction, and as you know, the mole fraction is defined as the number of moles of anhydrous lithium bromide to the total number of moles in the solution. And you can easily establish a relationship between the mole fraction, masses and molecular weight like this. The number of moles of lithium bromide is equal to mass of the lithium bromide divided by the molecular weight of anhydrous lithium bromide, and number of moles of water vapor, water is equal to mass of the water divided by the molecular weight of water. And for calculation purposes, you can take the molecular weight of lithium bromide as 86.8 kg per kilomole and molecular weight of water as 18 kg per kilomole. Now let us look at vapor pressure of water lithium bromide solution. This is required for calculation purposes, and I have discussed in the last class that one can use Raoult's law for ideal solutions, and from Raoult's law the vapor pressure of lithium bromide water solution is simply equal to Pw into 1 minus x, where Pw is the saturated pressure of water at that particular temperature T, and x is the mole fraction of lithium bromide. So 1 minus x is the mole fraction of water in the solution. So vapor pressure is simply equal to the product of saturated pressure into the mole fraction of water vapor. But we have seen that water lithium bromide solution deviates strongly from Raoult's law, and this deviation is a negative deviation. Let me give a small example. At 50% mass fraction and 25 degrees centigrade, Raoult's law predicts that the pressure, vapor pressure is equal to 26.2 millibar, but actual measurements of the solution show that the pressure is 8.5 millibar. That means the actual pressure is much less than the pressure predicted by the Raoult's law. This is because of the negative deviation of this solution from ideal solution, and the ratio of the actual vapor pressure to that predicted by Raoult's law is known as activity coefficient, and for this particular mixer you can see that the activity coefficient is much less than 1. The vapor pressure data for water lithium bromide solution is available in the form of empirical equations, and it's also available in the form of charts. Let me show a particular few charts. What I have shown here is known as a During plot. Here you have solution temperature on x-axis and the saturated temperature of pure water on one y-axis, and you also have on the left hand side of the y-axis the vapor pressure. Okay, and you can notice here that the x-axis, that is the solution temperature, is linear. Similarly, the saturation temperature is also, the scale is linear, whereas the vapor pressure scale is non-linear. You can see that the difference is varying. Okay, and you can also see on this the data is available for different constant concentration lines. These are the constant concentration lines. Zeta is the concentration, and the concentration increases in this direction. And if you are assuming, if you are taking this to be pure water, then here zeta is 0 and zeta increases in this direction. This particular plot is known as During plot, and this plot can be easily used for obtaining the vapor pressure data. You can also use other charts. For example, let me show one more chart. This is another chart where again the same information is available, but here on the x-axis you have the concentration of lithium bromide in percentage. Okay, this is mass fraction of lithium bromide in percentage, and on right hand side of the y-axis you have vapor pressure, and on the left hand side of the y-axis you have the saturation temperature of pure water. And here the data is available for different constant solution temperature lines. You can see that the 5 degree, 10 degree and all that are constant solution temperature lines. And also indicated here is how to find out the data. For example, if you have a 59% solution, you can see that this is the line, 59% solution line. At 59% concentration and 80 degree solution temperature, you will find that the vapor pressure is equal to 7.38 millibar, and the corresponding saturation temperature of water is 40 degree centigrade. Okay. Likewise, you can find out at other conditions what is the vapor pressure, or at a given vapor pressure and solution temperature what is the lithium bromide percentage, etc. Okay, these charts are very useful in actual calculations. The charts such as During plot is convenient for finding the vapor pressure data, and it's also convenient for showing the operating cycle. Normally the operating cycle can be shown on a During plot. Various component exit and entry points can easily be represented on the During plot. Now let us look at another important property, that is the enthalpy of water lithium bromide solution. Since strong water lithium bromide solution deviates from ideal solution behavior, you will find that the enthalpy equation is given by the following formula. Specific enthalpy H is equal to zeta into HL plus 1 minus zeta into HW plus delta H mix, where zeta, as you know, is the mass fraction of lithium bromide, anhydrous lithium bromide, and HL is the specific enthalpy of anhydrous lithium bromide at that particular temperature, and 1 minus zeta is the mass fraction of water, and HW is the specific enthalpy of water at that particular temperature, and as you know, delta H mix is the heat of mixing, and in this particular case heat of mixing is negative because this particular solution deviates in a negative manner from the ideal solution. Okay, that means the mixing process is an exothermic process. So when you mix water with lithium bromide solution, heat is generated. And enthalpy data, just like your vapor pressure data, enthalpy data for solution is also available in the form of empirical equations and charts. Let me show a typical chart here. Okay, so this is a typical enthalpy concentration temperature chart. You can again see here that the x-axis is the concentration or zeta in percentage. Okay, on y-axis you have the enthalpy of the solution, and this data is available for different solution temperatures. You can see that 25, 30, 40. These are all the constant solution temperature lines. So using this chart, again you can find out, for example, if you know, let us say 55 is the concentration, or 55 is the mass fraction of lithium bromide, and let's say that your temperature is 80 degrees. Okay, so you have to go like this, and you can find out what is the corresponding enthalpy. Okay, remember that specific enthalpy and internal energy and entropy do not have absolute values, or at least the enthalpy and internal energy do not have absolute values. So we have to define some reference points. So this particular chart is for the reference points like this. the specific enthalpy is taken as 0 kilojoule per kg for liquid water at 0 degree centigrade and for anhydrous lithium bromide at 25 degree centigrade. That means taking the specific enthalpy of liquid water as 0 kilojoule per kg at 0 degrees and anhydrous lithium bromide 0 kilojoule per kg at 25 degree centigrade, this particular chart is drawn. Now we also need in the calculations enthalpy of pure water, both liquid water as well as vapor at any temperature T. For liquid water you can have an approximate equation, the liquid water enthalpy is equal to 4.19 into T minus T reference, where 4.19 is the specific heat of liquid water, approximate value, and T is the temperature at which you are finding the enthalpy, and T reference is the reference temperature, and it happens to be 0 degree centigrade here, and the units here are kilojoule per kg because the specific heat is in kilojoule per kg. Similarly, you can have an approximate equation which is quite good for practical purposes for superheated vapor. For superheated vapor, the enthalpy is given as 2501 plus 1.88 into T minus T reference. Again here T is the temperature at which you are trying to find the specific enthalpy of water vapor, and T reference is the reference temperature. This particular equation is valid for water vapor at low pressures, and in fact if you look at this equation you will find that this 2501 is nothing but the latent heat of vaporization for water at 0 degree centigrade, and 1.88 is an average specific heat for water vapor. Now let us look at one typical problem associated with water lithium bromide systems. This is known as crystallization. In fact, if you noticed it on PTX and HTX charts, crystallization lines are shown. Let me show them again. You can see here that this line is a crystallization line, and below this the data is not given, and simply it is mentioned that it's crystallization. Okay, so this is a zone of crystallization. Okay, or crystallization zone. What do you mean by crystallization zone? Crystallization zone is a two-phase region. Okay, when the solution enters into this crystallization zone, in order to be at equilibrium, some lithium bromide from the solution separates out as solid crystals. That means in the crystallization zone you have a two-phase mixer consisting of lithium bromide water solution plus anhydrous lithium bromide in crystal form. Okay, so this is the meaning of crystallization zone. Okay, crystallization has practical significance in the design of water lithium bromide systems, because during the operation of the system, if the working fluid or the solution enters into crystallization zone, so lithium bromide separates out into solid crystals, and solid crystals can block the pipes and valves, etc. So they can hamper the performance of the system. So normally all practical water lithium bromide systems operate away from the crystallization zone. You have to design and you have to maintain the system in such a way that you don't enter into this crystallization zone. Okay. Same thing is shown in HTX chart also. Again in the HTX chart, this is your crystallization zone, and you should operate your system away from the away from this crystallization region. Okay. So as I mentioned, the region below the crystallization lines indicates solidification of lithium bromide salt. In fact, it is called as a slushy region because in this particular region you have a two-phase mixer which is a slush of water lithium bromide solution and crystals of pure lithium bromide, and they exist in equilibrium. And system should be operated away from this region to prevent formation of solid crystals which block the flow. Now let us look at steady flow analysis of a simple single stage vapor absorption refrigerant system based on water lithium bromide. And first let me list out the assumptions made. The first assumption is a usual assumption, it is a steady state and steady flow process. Then changes in potential and kinetic energies across each component are negligible, and there are no pressure drops due to friction, and finally only pure refrigerant boils in the generator. And the nomenclature followed here is like this: M dot stands for mass flow rate of refrigerant, M dot with subscript SS stands for mass flow rate of strong solution. Strong solution here means strong in lithium bromide. Okay, that means it is rich in lithium bromide, or in other words, the concentration of lithium bromide is higher. Okay, and M dot WS stands for mass flow rate of weak solution. That means weak in lithium bromide. Okay, and here we define another parameter called circulation ratio lambda, and this circulation ratio is defined as the ratio of mass flow rate of strong solution to the mass flow rate of refrigerant. Okay, lambda is equal to M dot SS divided by M dot. That means the mass flow rate of strong solution is simply equal to a product of circulation ratio into mass flow rate of refrigerant. And the analysis is carried out by applying mass and energy balance across each component of the system. So let me first explain the system, and let me give the equations. So as you have, in fact, you might have noticed that in the last lecture I have explained the basic vapor absorption refrigerant system. So let me once again explain it briefly. Here you have 4 basic components. This is the absorber, A is the absorber, E is the evaporator, Z is the generator, and C is the condenser. In addition to that, you also have refrigerant expansion valve here, and solution expansion valve here, and a solution heat exchanger, which as you know is used for improving the performance. And in addition to this, we also use a solution pump here. Okay, so let us again begin at this point, which is the exit of the evaporator. At the exit of the evaporator, as you know, you have low pressure, low temperature refrigerant vapor. This low pressure, low temperature refrigerant vapor enters into the absorber, where it comes in contact with the strong solution. Okay, strong solution that is coming from the generator. Since this strong solution has affinity for the water vapor gets absorbed here. Okay, and what forms here is a weak solution or a dilute solution. Okay. So the liquid, it is actually the solution is sprayed into this chamber, so that you divide the solution into fine droplets, so that there will be good heat and mass transfer. Okay, and this process, as you know, is exothermic, so heat is released, and this heat is taken out by circulating cooling water through this coil. Okay, and QA is the heat released during this absorption process. Okay, so due to this absorption, what forms is a weak solution? This weak solution is at low pressure, and it is pumped using this solution pump. Okay, so the solution pump increases the pressure of the solution, and this high pressure solution now flows through the solution heat exchanger here, where it exchanges heat with the hot solution coming from the generator, and it becomes heated up, and this hot weak solution enters into the generator. In the generator, you have to supply heat. Okay, heat can be supplied in a wide variety of ways. We will see how heat can be supplied, but at the moment let us assume that we are somehow supplying the heat required, heat QZ. Okay, so when you are supplying QZ to this weak solution, vapor is generated. Okay, so this vapor flows into the condenser. Okay, this is the vapor flow to the condenser. In the condenser, the vapor comes in contact with the cooling water coils. This is the cooling water coil. Okay, and the vapor condenses. Since condensation is again an exothermic process, here heat has to be taken out. So the cooling water takes the heat of condensation out of the system. So what you have here is pure water in liquid form. This is still at high pressure, so the pressure has got to be reduced. So this water flows through this refrigerant expansion valve, where it undergoes pressure drop, and this low pressure water is now sprayed into this evaporator. Okay, again you can see that it's sprayed into the evaporator. When it is sprayed, the liquid droplets fall onto this chill water coil. This is a chill water coil. Okay, and as it falls on the chilled water coil, it evaporates. So as a result of it, since evaporation is endothermic, the water that is entering into this gets cooled. So ultimately what you get out of this is a cold water. Okay, that is nothing but your refrigeration effect QE. Okay, and during this process liquid becomes vapor, and this vapor goes to the absorber, and thus the refrigerant cycle is completed. And as far as the solution is concerned, you remember that at the exit of the generator you have strong solution. That means solution that is rich in lithium bromide. It is at high pressure and it's hot. Okay, now it flows through this heat exchanger again, where it exchanges heat with the weak solution, and its temperature reduces. Since it is still at high pressure, it is expanded through this solution expansion device, and its pressure drops. and its pressure drops to that of the absorber pressure, and so this low pressure rich solution is again sprayed into this absorber, and the solution cycle is completed, and this process goes on. This is the simple single stage vapor absorption refrigerant system. So what we will be doing is we will be applying a steady state steady flow analysis to this system to arrive at expressions for COP etc., COP, mass flow rate etc. Okay. So what we will do typically in a steady state steady flow